Hello YouTube, I'm back with another episode of the Everglory Devlog. This episode is going to be all about the formation system, and I'm just going to very quickly tease it.
Бьемся до конца. Мой друг голоден. Не отведут мое копье.
So, as you can see, it basically allows me to group a number of different units into a formation of one of a few different types, and the units will move together in a formation as well as arrive at their destination organized in the said formation. And later in the video I'm going to do a deep dive into how it all works, just look at the different edge cases, how the units handle static obstacles, dynamic obstacles, and really go deep into the algorithms that are running behind the scenes powering everything that you see here. But before we get into that, I just wanted to do a quick progress update of the game and the engine. And here you can see the brand new Teutons faction. This is the third and final faction in the game. We've got the Knight unit, the Teutonic Cavalry unit, and last but not least, the Panzer Crusader. And if we go into the settings here, we now have the option to play the game more zoomed out, see more of the map at once. Let's go to 150%, and here we can see just how many units we have on the map right now. This is 400 units, and if we go, make them battle each other, you can see that 400 units in a single battle runs at a very acceptable FPS.
Back on my bullshit. Back to back on my bullshit. Matter of fact, that was bullshit. I'm going back to back on my bullshit. Do it one time, they gon' think it's luck. Gotta hit them with the repeat. Do it two times, they gon' still doubt. Hey, now I got a three-peat. Gotta flood the streets till they knee deep. Gotta stay woke, can't be sleep. All this fly shit don't be cheap. All these bad bitches that we keep round. Pockets gotta be deep now. Never lose again, living me deep down. Gotta keep winning, it's a clean sweep now.
So now let's look at some of the details. The first question is, what's going to happen when the units that are in a formation encounter obstacles along their path and nearby the location where they're told to go to? And let's see what happens.
Разорвем их на куски.
So the answer to that is, it's handled in my system. They will go around the obstacles, and when they're being placed around their target point, they will be placed around the obstacles.
Время воевать. Погибну героем.
The next question is, what's going to happen when this relatively wide formation is told to go through a narrow choke between two cliffs? Let's just see
Разорвем
what
их на
happens.
куски.
And the answer to that is that they will break formation for the time that they're going through the choke, and upon coming out of the choke, when they're able to, they will reorganize themselves in a formation.
Погибну героем.
But here we'll see one limitation is that the units are not forced 100% to stay in formation. They have an affinity to kind of stay in formation as much as possible. But what that results in is that they're not as tightly packed, they are not as organized as is theoretically possible when they're moving. There is more room to address that. However, I'm pretty content with the way it is right now. The next question: what happens when units in a formation encounter dynamic obstacles? Say they are heading towards another group of units that is moving in the opposite direction, and let's just see what happens.
Победа будет наша. Заслужим славу.
And the answer to that is that the units will not collide, they will not make some kind of traffic jam, rather they will form kinds of
Вперед!
lanes.
Заслужим славу!
I think it's a very nice looking result. Here, let's look at some more examples. These units, let's tell them to go behind these huts.
Борюсь до последнего дыхания.
It's another very nice looking result. There's some gaps in between them, and the units will go through the closest gap. Upon exiting the chokes, they will reorganize themselves.
Борюсь до последнего дыхания.
Furthermore, in the current system, it's possible to have different kinds of units together in a single formation. They have different types of units have a priority, so cavalry will be at the front, ranged and support units will be at the back, and they are able to move together as a single formation. Now let's look at some more less obvious cases that aren't so easy to handle. So one example is like a sharp turn for the formation. Say we wanted to turn 90 degrees. Let's see what that looks like. Although there's a little bit of quirkiness at one point, I think generally it's pretty acceptable. Now let's look at another interesting case where a formation is asked to reverse. So now these huts are at the back, these foot soldiers are at the front. Now let's make it face in the opposite direction. And we're going to see that, the huts, they reach their target positions first, and these foot soldiers, in a relatively intelligent manner, they'll go around the huts and reach their target positions. So there's one final case I'm going to touch upon, and that's when you have a simple formation consisting of just one type of unit and you rearrange them, such as you make them face into a different direction, as we see here, or also when you go from a rank formation to a column formation. And what we see here is that there's no crisscrossing of the units, there's no bumping of the units into each other. The relative position of the units within the formation is recomputed, such that the total distance traveled by all the units together cumulatively is minimized. So that leads to an optimal rearrangement, and that also leads to the minimum number of path crossings between the different units. So what makes this look quite pleasant is the fact that there's no traffic jams, no crisscrossing of the units' paths. And in the next part of the video, I'm going to just outline the algorithms on paper, and then I'm going to come back into the engine and show a whole bunch of debug visualizations that hopefully give you guys a good glimpse of what's happening behind the curtain. Here's just a quick little tease of that. So now I'm going to outline the actual algorithms that are being used to power everything you saw in the earlier demo. First things first, I'm going to outline the data structures that are being used in the code to model the formations. So in my approach, every formation is a set of subformations. The subformations maintain a relative order to one another. So keeps track of which ones are at the front, which ones are at the back. Every subformation holds all the units of a particular type. For example, all the foot soldiers are in one subformation, all the archers are in a different subformation, and every subformation has a 2D array of cells, the dimensions of the array being such that there's enough cells to give one cell to every single unit. And every unit within a subformation is then assigned to a single cell. So it would look something like this. Say we have some arbitrary group of units, some archers, some warriors, some knights. Then there's 3 types of units. 3 subformations would be created. The first subformation for the knights, which are at the front, there's 2 cells. Second subformation for the warriors, which are in the middle, there would be 8 cells, which is enough to hold the 7 warriors. And the priority of the different kinds of units, they're just metadata that's a part of the game. So the whole problem of units being organized into formations, moving together in formations, being positioned appropriately relative to the formation's target position, it's a very big and complex problem. So it's helpful to break it down into a number of sub-problems. The first sub-problem is the cell placement problem. Basically, when we have a set of cells, how do we place them onto a map such that no cells overlap with each other, no cells are on top of any obstacles, and furthermore that the cells most closely resemble a perfectly organized grid that they would be in if there were no obstacles whatsoever. Secondly, it's assigning every unit to a specific cell, but doing the assignment in such a way that the path crossings between units are minimized. And lastly, when we have placed the cells on the map, we have assigned units to the different cells. How do we make the units move, march across the map, and maintain as much as possible their place in the formation in the presence of various dynamic obstacles? So let's start off with the cell placement problem. Here are formation data structure, and in my game engine the map is modeled as a 2D array of tiles, a grid of tiles. And first of all, we have to pick a target and an orientation for the formation. For example, the user clicks and holds and drags the mouse. He picks a point on the map and a direction for the formation. Then we have to place every cell in every subformation on the map. In the absence of any obstacles, in the simple case, this is a very simple problem. It's just a couple of for loops. Also want to mention that there's freedom in how you place the cells. For example, if you want to put gaps between the different subformations, there's nothing stopping you from doing that. But now we come to the interesting case. What do we do if there's some obstacles in the immediate vicinity of our target point, such that we are not able to place subformation cells in their natural position? And the approach to solve that is to essentially place the cells in a very particular order and place every subsequent cell relative to cells that have already been placed. So we would place the units, roughly speaking, from the front to the back. More specifically, we would first place all the units in subformation 0, then subformation 1, and so on. Furthermore, within every subformation, we would place the units in a specific order. So for every subformation, we pick a root cell. That's basically the centermost cell of the front row. In the case where the number of columns is even, it would be the closest cell to the centermost cell in the front row. And then within each subformation, we would start by placing the root cell, and then we would place the cells closest to the root cell, going out in a breadth-first manner and placing cells that are further and further away. So let's quickly go through a simple example. We have our formation with 3 subformations. We start off by placing subformation 0. The tile for cell 0 is free, so cell 0 just goes there. It's simple. Now we go to placing cell 1, and we want to place this relative to cell 0. So we want to place it to the right of cell 0. That would go right here, but we notice that this tile is already occupied. So we have to use some kind of algorithm to pick the next best suitable tile for this cell. In the simplest case, it could be just a basic breadth-first search, and say we have a breadth-first search where we test the left tile first. It would just end up being to the left. And also want to mention there's room to improve on the simple breadth-first method, essentially to give a sort of priority, a sort of affinity for the cell to be placed still relative to the earlier placed cells. For example, potentially, in another implementation, it will be possible for cell 1 to be placed here to the right of cell 0, just skipping over these 2 obstacle tiles. Afterwards, we have placed subformation 0. We go on to place subformation 1. So cell 0 is, we want to place it behind the center of subformation 0. That tile is free, it goes there. Then we want to place cell 1 immediately to the right of cell 0. But we notice that's blocked, so it would end up going to the left instead, following our breadth-first search method from subformation 0. Then we want to place cell 2, and we want to place cell 2 to the left of cell 0, because that cell immediately to the left of cell 0 is already occupied by another tile. We go on to find the next best appropriate tile, and we place it to the left. And then we want to place cell 3 immediately behind cell 0. That tile is free, so it goes there. Then cell 4, we want to place it both behind cell 1 and to the right of cell 3. So behind cell 1 would be there, to the right of cell 3 would be there. And on average, the average position would be exactly where cell 3 is already placed. And since we cannot place the cell there, we find the next closest tile. For example, it could be, using a breadth-first search method immediately behind cell 3. And now I'm not gonna go through all the details. I think you guys get the main idea. We place the rest of the cells. Next up, we want to place subformation 2 immediately behind subformation 1. But what does it mean in this case, immediately behind? And we can define behind as behind the average position of the back row cells. So if we find the average position of cells 5, 3, 4, 7, and then go one behind it, it would be, where, right here, where cell 0 of subformation 2 is placed. Then cell 1, we want to place it to the right. That's blocked, so it would go immediately to the left. And I think this overall high-level idea, it works pretty well for placing the cells. Basically, you use a greedy algorithm where you place the cells one at a time, starting from the front to the back, within each subformation going outwards from the center front position. That in general leads to pretty good looking placements where both there is handling of obstacles, and at the same time, as much as possible, units maintain their relative position within a formation. So moving on to the next subproblem, assigning units to cells. And here we have a set of units. They can be in arbitrary positions on the maps. They can be arranged in a formation already. They cannot be, for the purpose of describing the most general case, let's say their positions are completely random. And we have to basically, compute an assignment from their existing positions to target cell positions such that, broadly speaking, it's the most intelligent looking assignment such that units don't end up going to a cell that's way on the other side of the formation, that they don't end up crossing each other's paths, bumping into each other, and so on. For example, here this knight is more left of this knight. So it would make sense for this knight to be assigned to the leftmost cell and the other knight to be assigned to the rightmost cell. And I think we can identify that this unit to cell assignment problem is an instance of a more general assignment problem. It could be units to cells, it could be workers to jobs. It's just a reskin of the same problem. Essentially, it's a combinatorial optimization problem where we have to find a maximum or a minimum. And if we just look at this problem as purely a geometry problem, then we can express it in the following manner. So we have two sets of points. In this picture, they are the blue points and the red points. And we have to pair up red and blue points in such a way that the distances in each of the pairs, the overall cumulative distance is minimized. And an important result of that, an important property of an optimal solution is that line crossings in the optimal solution will also be minimized. This is a so-called Euclidean assignment problem. And if we were to map our unit assignment problem to this problem, then the current unit positions would be the blue points and the target cell positions would be the red points. And fortunately, there's already a well-known algorithm for solving this exact problem. It's called the Hungarian algorithm. I'm not going to talk in detail about it in this video, but just make note of the name. There's a lot of work, describing this algorithm already. In brief, the input to this algorithm is the set of distances between every unit to every possible cell that it can go to. And the output of this algorithm is an assignment, a set of matchings between units and cells. So once we have placed the cells and we have assigned a unit to every single cell, what's left to do is just give every unit a move order to go to its target cell, and they would be arranged in a formation. In a simple game, this is just sufficient, but to support both very large maps and at the same time very high unit counts, we have to take some care with how we give these move commands. So we do not want to be computing a separate A-star path for every single unit, because with sufficiently large unit counts, that would quickly get out of hand. So recall that permafrost engine uses flow field pathfinding. I'm also not going to talk about it in great detail in this video. I talked about it in more detail in episode 3 of the devlog. But essentially, it's a system where instead of computing a separate path for every single unit, I compute a single field for the map or a subregion of the map, and this field will guide, it's like an attraction field that guides anything caught in this field towards some target point or set of target points. And now, what I have to do, or what I've done already, is amend this system in such a way that instead of going to a single point, a group of units will rather go to a set of distinct points, their target cell positions. And obviously, it would be undesirable for me to compute a separate field for every single unit. That's just not very scalable. So the approach I took is basically to define some proximity region nearby the flux target point. And this region has to be large enough such that all the cells can fit inside this region, and there's also some breathing room around the cells. So some care needs to be taken to pick the appropriate size of this region. But essentially, when units are outside of this proximity region, they will go just towards a single point. Essentially, they will use one field, one path to go to just the formation's target point. But only when they are inside the proximity region already will they be guided by a smaller field towards their cell position. So for example, in here we have 4 different units. We will use one big field to guide the units inside the proximity field, and once the units are inside the proximity region, they will use a separate cell arrival field to arrive at their cell position. So here would be one large field and 4 smaller cell arrival fields. And I want to just point out kind of a subtle but important observation that can be made here. So each of these cell arrival fields for the different units will have a distinct set of kind of natural rows and columns that the units will tend towards when they are inside of this field, with the target cell tile being in the crosshairs of this at the intersection of this row and column. And essentially, when a unit enters this proximity region and it starts using the cell arrival field, it will be guided towards its natural row or column, into one of these lanes going towards the target point. And so for example, if a unit enters this proximity region from the top, it will have a tendency to go down until it reaches this lane. Similarly, if it enters this region from the bottom, it will have a tendency to go up until it reaches this lane where it will no longer be pushed up or down. And this actually ends up having a very positive result in terms of making the units stay in formation when they are inside this proximity region, because just by natural forces, the units will be spread out into different lanes based on their cell assignment. So every unit will have a tendency to go towards its natural lane. And now I have to address a question some of you guys probably already have. So let's say I have hundreds of units. Wouldn't it be unacceptable for performance to compute this cell arrival field for every single unit? So first of all, the cell arrival fields are relatively small. So it's not too costly to compute a single field. Second of all, in my engine, I compute these fields asynchronously. So when I give a move order, I don't compute all 200 or 400 or however fields in that one frame. I simply kick off some background jobs, and when the field is ready, the unit will be able to use that field. And of course, that necessitates handling of the case where a unit is already inside the proximity region, but the field is not yet ready. And actually, there's quite simple ways to handle that. You know, the most obvious one being is just like wait until it's ready. It's like the unit will take a brief pause and then it will go. Something even better is just try going in a straight line towards the target position, and if we bump into a wall or some obstacle, we end up just waiting, but that's also quite unlikely. And practically speaking, I will say this works very well, and it's essentially invisible for the player. The fact that these fields take some time to be computed. The computation is quite fast, and at the same time there's a natural kind of grace period for this computation when the units are slowly moving towards or into the proximity region. Now I have to give due diligence and address another problem case. So we give this move command, we compute the cell positions. What happens if before the unit has time to arrive at its cell position, the tile gets blocked, the cell gets blocked? And this is a very fundamental problem in RTS pathfinding in general, right? The map conditions are changing dynamically. There's a lot of units, they're starting, they're moving, walls are being built, walls are being destroyed. So paths that were valid last frame suddenly become invalid. And there's basically, the solution to this problem is to, the fundamental solution is to recompute the field when necessary. And of course, we have to be careful to basically do the least number of computations and do it only when it's absolutely necessary. So we don't overwhelm the CPU with just constant recomputations of paths. And keeping it brief, I have some logic in my engine to detect when a tile has become blocked off or unreachable, and in that case, also done fully asynchronously, this cell arrival field is recomputed. If necessary, the blocked off cell is repositioned to its closest possible reachable position. So moving on to the final subproblem, we have to answer the question, how can the units stay in formation when they're outside the bounds of the cell arrival field? When they are moving through the flow field to a single target point, how can all the units maintain their relative position to the formation origin? And recall that the engine uses flocking behaviors, aka voids, to make the units move as a flock, as a sort of death ball through the flow field. And briefly describing the system, there's a number of forces, mainly the separation, alignment, and cohesion forces that act on every single unit that's in motion. The separation force prevents the units from stacking up. The alignment force makes them have a tendency to all face in the same direction, and the cohesion force attracts them to the center of mass of the flock, which is what gives this ball effect. And the beautiful part of this approach, of this algorithm, is that it's able to handle any dynamic conditions that you throw at it. What I mean by that is that, for example, take the cohesion force. When the units move through an empty field, the cohesion force keeps them together as a ball. When the units reach a choke point where the whole ball cannot fit through it, then the cohesion force will still act on all the units, but other forces will overpower the cohesion force, thereby making it irrelevant, and causing the units to temporarily break the ball structure. Upon exiting from the choke, the cohesion force will become relevant again compared to other forces that are also acting on each entity, and the units will ball back up. And the fundamental idea, the fundamental approach is to extend on this idea of per unit forces. And instead of using the cohesion and alignment forces, which cause the units to form a sort of a death ball, instead to change and amend these forces so that the units rather have a tendency to maintain a formation structure. And the approach specifically that I took is to pick a leader in each subformation. This leader is the same as the root cell from the earlier described placement algorithm. It's the centermost unit in the front row, and this unit, the leader, will determine the overall alignment or orientation of all the units in the formation. So all the other units will have a desire to face in the same direction as the leader as much as possible. Furthermore, we compute a set of slot locations relative to the leader's current position. And all units in the front row of the subformation will have a force guiding them to their target slot location. So for example, units that are ahead of the leader will have a drag force slowing them down until they are aligned with the leader. If a unit is, say, too far to the left, it will have a force, slowly, gently guiding it to the right until it is aligned vertically with its target slot location. Units that are not in the front row, back row units, and all intermediate row units will have a chasing or following force that will make them, as much as possible, trace the path of the unit immediately in front of them in the formation. And I think, in principle, this approach is quite good, but in the version that I have realized so far, this works with some limitations. In basic cases, it works pretty well. However, when you take a large army consisting of different units of different sizes and you really stress them on a long path, you make them turn and rotate and go through chokes and go out of chokes, then it will be difficult for them to reestablish their initial formation structure. So there's definitely some room for improvement. And I have some ideas, but I just have not had the time to get around to testing them out, experimenting with them, and implementing them thus far. So first of all, there's some room to play around with the different parameters of the forces, like adjusting the relative strength of the forces, the radius of the effect of the forces, and so on. As well, I think potentially a slightly better approach would be to make the back rank units also have an affinity to go towards a slot position relative to the leader's position rather than trying to follow the units in front of them. And lastly, a more interesting idea that I had is based on the observation that these different lanes that kind of emerge when you have cell arrival fields guiding units to different cell positions, they work quite well at splitting up the units into different lanes when they are within the proximity region. So one potential clever solution would be to establish a set of intermediate points along a formation's path, and basically instead of going directly to their final destination, the units would go to checkpoint A, then to checkpoint B, then to checkpoint C, and so on until they go to their final destination. And at each checkpoint, the units would not even stop. Rather, seamlessly, they would transition to moving to the next checkpoint. And in theory, this should have an effect that at each checkpoint location, the units would more or less be in a formation, as at least as much as possible as placed by as determined by the cell placement algorithm. And I think this has some potential, but definitely already I see there's a ton of bullshit edge cases that would need to be dealt with. It overall is, a very sophisticated system, so it's something that needs to be experimented with, tuned with, debugged for a long time, and I simply just don't have the time for it at the moment. So it's something I kind of have left on the back burner as a future enhancement that potentially at some point I can get back to. And now for the final part of this video, I'm gonna go jump back into the engine and I'm gonna show you guys some visualizations that show and demonstrate all the algorithms that I described in this presentation working in real time in the engine. To quickly mention a detail of the engine, there is a blockers field that's maintained for all tiles that are blocked. Furthermore, as I mentioned in one of the earlier devlogs, I have different navigation layers to support units of different sizes moving more intelligently. So first, let's take a look at cell placement. And here, the cells are placed using roughly the same algorithm that I described earlier in the presentation, and for the majority of cases, it looks pretty good. The semblance of the formation structure is there. There's some gaps around obstacles. Say we place the units in a choke, they will fill up part of the choke and kind of spill out. But when it's an open field, they're able to be arranged into a perfect grid. Now, another detail is assignment. So here we see the result of the Hungarian algorithm. We see that we can appreciate that there's no crossing of these pink lines, essentially. The units will go to their optimal position. Next up, let's look at cell arrival fields. And if we pause the game for a second, if we zoom out, we can see that The field is approximately, or it is this large, just a small subset of the map. It will always be this size regardless of the map size. And if we cycle through the fields for the different units, we can see that we can kind of observe these lanes. And again, that was done completely asynchronously. If I hadn't told you guys, you would have never known. And
Не отведут мое копье.
last but not least,
Погибну героем. Время
let's look
воевать.
at the forces. So
Мой друг голоден.
this is the leader with the green circle around it.
Мой друг голоден.
Units which have a red circle around them, they're experiencing a drag force, so they want to slow down a little bit, let the leader catch up to them. I make it so units can never speed up past their maximum movement speed. That will kind of be,
Погибну героем.
cheating in a way.
Погибну героем. Заслужен славу.
So that's it in a nutshell. Of course, there's a lot of small details that are part of the implementation that I just don't have the time to get into in this video. I think it's already long enough, but I just want to remind you that Permafrost Engine is fully open source. If you really want to study the code in detail, it's available on GitHub. You can download it, play around with it, so forth. That's it for this devlog. I hope you guys found this useful and interesting. If you want to support the project, please wishlist Everglory on Steam. Drop a like on this video. Subscribe so you don't miss my next updates. And I'll see you guys in the next devlog. Peace.
Yeah, I cannot bullshit with none of y'all. I got a bullseye on some of y'all. I feel like Michael in 95. Back on my bullshit this summer, y'all.